Okay, forgive me there. Just wanted to make sure the camera was actually working, which can be problematic. Now, supposing I'm from another planet, and I don't know whether males or females are taller in the class. And so I'm just going to hypothesize that there's a difference between males and females. And I'm going to hypothesize that that difference is significant at the 0.05 level. I have to split my level of significance to either end of the tail, the low extreme and the high extreme. I have to put half of it here, which is p equal 0.025, and p equals 0.025 here. Now I'm going to do the same thing that I had done before. I'm going to gather my data, and then I'm going to enter it into a statistical analysis, and it's going to yield a test statistic and an associated p-value. Let's just say that it yields a p-value of 0.01. And we can see that the p-value that was generated by the analysis is lower than our 0.025. It would be somewhere in here. And because it's low, we are going to say that the null must go. If p is low, the null must go. So my hypothesis is that there is a difference, and my analysis has confirmed that yes, there is a difference, and it has also shown me in which direction this difference lies. Okay, kind of test where you don't know whether your difference is going to be high or low is called a two-tailed test. And in a two-tailed test, you have to split your level of significance to either end of the extreme of the distribution of data. Okay? All right, now let me back up just a little bit and say something once more about quasi and non-experimental. I had told you at the beginning of the earlier portion of this video that the difference between quasi and non-experimental lies in control. If controls are up, it tends towards the quasi side. If controls are diminished, it tends towards the non-experimental side. Now, what is the biggest thing that you can control? The biggest confound in quantitative research is the possibility of systematic differences in your sample. Now, if you have systematic differences between your treatment group and your control group, well, the results may be because of those systematic differences. Supposing you ended up in randomly, just by chance, with a control group that had 85% females, and your treatment group, just by chance, had 85% males. It could be that gender is the deciding factor here, a systematic difference in our samples. So, the biggest thing that one tries to control is systematic differences in the sample and in groups. How do we control systematic differences in our groups? Well, there's three ways to do it. And this is one of the factors that you will use to differentiate between quasi and non-experimental quantitative research. Okay, the biggest problem we have, systematic differences in our sample or in our groups, control group and treatment group. Now, to control for systematic differences between our sample and the population, the biggest, most effective, and most commonly used ploy is random selection. True random selection means taking from a population one member wherein every member has an equal opportunity to be chosen. So pulling one out, recording who that is, subject number 72653A or whatever, okay, then before you draw another subject, you have to put that one back. If you don't put that one back, you have changed the odds of each person being selected. For example, if I have, let's just say 100 in my population and I want to draw a random sample. If I pull one out, this person had a chance of 1 out of 100 of being selected. Now I record that person's identity, okay? If I don't put this person back, if I leave him over here, now I have 99. And the odds of pulling anyone out of that population to be a member of my sample is now 1 out of 99. This precludes randomization. So you have to take this person and put them back in the sample. Okay? So that every single person has the possibility of being chosen, an equal possibility of being chosen, 1 out of 100. Now supposing you pick the same person, you simply put them back and pick another. Okay? But each time you choose one from this population to be a member of your sample, you have to replace them. That is called random selection with replacement, and that is true randomization. It's thought that if you randomly select people, you are going to get somewhat of an even distribution of variability within personality or traits or whatever it is that you are concerned with in your research. The larger your sample, the more likely your sample is to reflect the true nature of your population. Now remember, sample size has many considerations. You know that there is a diminishing return after about 30. A good number for a study is actually between 20 and 100. 20 or 30 is adequate. Beyond 30 or 100, you get diminishing returns in ability to be able to discriminate in your results statistically. You get diminishing returns. In fact, if you have a sample with thousands of members, it is possible that you may come to the conclusion that something is statistically significant, but the difference is so tiny that it clinically is irrelevant. Okay? Now, randomization is one way to ensure control of systematic differences between your sample and the population that you're drawing from, and also random assignment into control or treatment group is a way to account for systematic differences as well. That is the #1 ploy. There are other ways to do it. You can match members, match variables. For instance, you have a sample and you want to compare this 22-year-old male with this 22-year-old male. You try to make the characteristics of the subjects that you are comparing as close as possible, hence matched. Another way is to hold a variable constant. Hold variable constant. Okay, now supposing you don't want 7-year-olds in your study, you don't want 85-year-olds in your study, you are looking for 20 to 25-year-olds, that is your target group. You can hold that variable constant, and that is a way also to mitigate against systematic variations between your sample and population, or between your control and your treatment group. So, one of the biggest characteristics, well, we've said, if controls are higher, it's more like a quasi-experiment. If controls are lower, it's non-experimental. The biggest thing we have to control are systematic differences between sample and population, or between control group and treatment group. 3 ways to control those: randomization, matching variables, hold variables constant. Now, there are some other ploys as well, such as stratification, to ensure that your sample is going to be similar to the population. And you can stratify between your treatment group and your control group as well. Stratification is rather simple. If you want to stratify by gender, you might ensure that knowing the population is 50-50, that you have a more or less 50% representation of each gender in the sample you've chosen. You can also then, in your assignment to treatment group and control group, make sure that you end up with 50% female here and 50% female in the other. So that's stratification by gender. You can do stratification by age, stratification by socioeconomic status as well. Now, so knowing that the biggest issue of control is systematic differences, one of the easiest ways to find out whether your research in question is quasi or non-experimental, if there is randomization taking place anywhere in the assignment of the subjects towards, or the participants, towards treatment and control group, it's going to lend itself towards the quasi-experimental side. Okay? So randomization of assignment to groups is going to be very important. Now, in a true experiment, you have to have randomization in the selection of your sample. Quasi-experimental research often deals with variables where you can't have random selection. Supposing you want to deal with cancer patients, you can't go manipulating cancer. You can't give people cancer in order to do a study on them. If you do want to do research with cancer patients, you can draw from a sample of cancer patients in a random manner, then randomly assign those to a treatment group and a wait list, and then do a true experiment. But if you are simply looking at cancer patients and the effectiveness of a treatment program, you cannot randomly assign that variable to people. It's unethical, to put it mildly. Okay, so I hope that clarifies some aspect of what is the most important aspect of control. The most important aspect of control in regards to internal validity, and of course external validity depends on internal validity, is randomization of assignment. With certain variables, that's impossible. Okay, then you're going to have quasi-experimental. If you have no randomization at all, you're going to end up with a non-experimental design. So I hope backing up that clarifies it a little bit more. Please come by between classes and ask me questions if you have any. Okay. Let me review once again that hypothesis testing. You know that neurons that fire together wire together, so the more often that you hear things or practice them yourself, the more likely they are to form permanent restructuring of your brain, neuroplasticity. So let's just take a quick review of hypothesis testing. HIP testing! Yay! Hypothesis testing. first thing you do, you need a hypothesis. But not just any hypothesis, it has to be testable. How are you going to make your hypothesis testable? By having concretized independent and dependent variables. They're going to have to be operationally defined. First step, testable hypothesis. Second step, choose your p level, level of significance. Choose p. Normally, it's going to be p less than 0.05. Okay, now, then you're going to gather data. Then you're going to perform a statistical analysis. Which analysis you're going to choose is going to be according to the level of data that you have, whether it's nominal, ordinal, interval, ratio, and the number of groups involved in your comparison. And I'm going to upload a chart which will give you a if this, then that sort of scenario for choosing the kind of statistical analysis that are commonly available. You do not have to understand the mathematics behind the statistical analysis for this purpose. Your statistical analysis, the most complicated thing that you're going to do after choosing it, according to the level of data and the number of groups, is going to be data entry into either the statistical package for the social sciences, SPSS, or one of the online calculators. And I'll give you an example of this so that you can follow the procedure later. The statistical analysis is going to yield a test statistic, and it's going to yield an associated p-value. You compare the p-value yielded by the statistical analysis with your chosen level of significance. And if p is lower, the null must go. P is higher, the null must fly. Then you're going to make a decision. If you understand this process of hypothesis testing, you understand most of quantitative research. You will be able to look at a quantitative study, identify the hypothesis, make comments about whether it is testable, whether the independent and dependent variables are concretized enough. You're going to see what levels of significance the researchers have chosen. You're going to see how they gathered their data. Then you're going to see that they have chosen certain statistical analysis, the mathematics of which you do not have to understand in order to understand that it will yield a test statistic and a p-value. Commonly, there will be a lot of dependent variables that will undergo analysis, and there will be many things, and they will state that scores on the Beck depression inventory were significant at a 0.01 level, which is lower than our chosen level of significance here. You're going to see that and be able to understand why they then rejected the null hypothesis and accepted the alternative. Okay, in the example that I gave before, the alternative hypothesis was that Beck's depression inventory scores would decline after cognitive behavioral therapy. And then you're going to make a decision based upon comparing the p-value that was generated by your statistical analysis, comparing it to your level of significance. Now, for most people, the very uncomfortable part of statistics lies right here. You don't have to be afraid of that part, okay? We have lots and lots of software that will do the analysis for us. The complicated part, number one, choose the correct statistical analysis. I'll give you a chart to help you with that, and again, it is done by the level of data that you have, nominal, ordinal, interval, or ratio, basically discrete or continuous, okay? And the number of groups that you need to compare in your analysis. that will tell you which analysis to use. Having discovered which analysis to use, find the software that will allow you to enter your data, push calculate. It will yield a test statistic and a p-value for each set of data that you plug in. Compare that p-value to your level of significance and make a decision to accept or reject the null. Now, this part of statistics is what makes people uncomfortable. Don't be afraid of that part, because you have software that's going to be able to do that part for you. However, for those of you who are so inclined, take my word for it that the long, complex-looking formulas that generate or are part of a statistical analysis are easy when you break them down. They do use some Greek terminology, or Greek letters like sigma, uppercase and lowercase, but all of the rest of it is very, very simple in looking at its parts. If you take it piece by piece, it's a piece of cake. Believe me, it is not prickly at all or hard to handle for those of you who are inclined to do so. It is, however, tedious, very, very tedious. Repetitive operations, and it will involve a lot of attention to detail, subtracting the mean of one group from the mean of another group and multiplying by the variance or whatever. But each individual process within the complex equations that have to do with statistical analysis are not difficult to break down. They are tedious. They may look weird, they may look very scary, but believe me, they are not. Instead of looking at those equations as something prickly made out of barbed wire, think of it as a puppy dog. Okay? Puppy dogs can be tedious. You have to house train them. You have to repetitively do things over and over after you feed them. After they take a drink, pick them up, take them outside, and praise them for defecating and urinating outside. Puppies are tedious. Statistical analysis is tedious too, but not difficult mathematically when you break it down piece by piece. So do not be afraid of those monstrous looking equations. Okay, view them as puppy dogs. Okay, that yes, they can be tedious, but they can be tamed. Okay, and you can house train statistical analysis. Okay, I hope this has helped. Don't be afraid to come by my class and ask questions. In fact, I'm going to be sending an invitation out to all of you who are taking this class online to come by for lunch on one of these days, so that we can chew over statistics. So I hope that this has been somewhat of a clarification for some of the things that we have been involved with. Take care.